Understanding fault current calculations is crucial in electrical engineering for ensuring safety in protecting equipment. Fault current is the amount of electrical current that flows during a short circuit condition. It is significantly higher than normal operating current and can cause severe damage if not properly managed. To accurately determine the fault current at a specific point in an electrical system, you typically need to know the system's voltage, the impedance of the components, and the available fault current at the source, such as the transformer. Let's clarify why knowing the available fault current at the transformer without knowing the impedance or kVA prevents you from calculating the fault current at a downstream location. The available fault current at a transformer's secondary terminals is the maximum current that the transformer can deliver during a fault condition, assuming a bolted fault at the terminals. This value is determined by the transformer's kVA rating and its impedance. The formula to calculate the available fault current at the transformer is based on these parameters. Firstly, you need to understand the transformer's impedance. Transformer impedance, expressed as a percentage, indicates the voltage drop across the transformer when it is delivering its full rated kVA. This percentage is crucial because it limits the fault current. A lower impedance allows for a higher fault current, while a higher impedance restricts it. Secondly, the kVA rating of the transformer defines its power handling capacity. A larger kVA rating generally means the transformer can supply more current, and thus potentially a higher fault current. The relationship between fault current, impedance, and kVA can be illustrated with the following conceptual breakdown. Let's assume you have a transformer and want to find the available fault current at its secondary terminals. You start with the transformer's kVA rating and voltage. You calculate the transformer's full load current using the formula kVA times 1000 divided by the voltage. For a single-phase transformer, you simply use the voltage. For a three-phase transformer, you use the voltage times the square root of 3, which is approximately 1.732. Then, you consider the transformer's impedance, which is usually provided as a percentage on the transformer's nameplate. This percentage impedance represents the voltage drop when the transformer is loaded to its full kVA rating. To find the available fault current, you divide the full load current by the impedance percentage. This gives you the maximum fault current that the transformer can supply under ideal conditions, which is a bolted fault directly at the secondary terminals. Now, let's address the scenario where you know the available fault current at the transformer but don't know the impedance or kVA. In this case, you cannot calculate the fault current at a downstream location because the available fault current is itself a result of the impedance and kVA. Without knowing these underlying values, you lack the necessary information to determine how the fault current will be affected by the impedance of conductors, circuit breakers, and other components in the electrical system downstream from the transformer. To further illustrate, consider a simple electrical circuit connected to the transformer. The circuit consists of conductors, overcurrent protection devices such as circuit breakers, and the load. Each of these components introduces impedance, which limits the fault current. The total impedance of the circuit is the sum of the impedance of the conductors, the impedance of the circuit breaker, and the impedance of any other components in the fault current path. Fault current at the load can be calculated using Ohm's law, which states that current equals voltage divided by impedance. In this case, the voltage is the system voltage, and the impedance is the total impedance of the fault current path. However, without knowing the transformer's impedance and kVA, you cannot accurately determine the starting point for the fault current calculation. The available fault current at the transformer is merely a single data point. It does not provide enough information to extrapolate the fault current at other locations in the system. To accurately calculate the fault current at a downstream location, you must perform a comprehensive fault current study. This involves collecting data on all the electrical equipment in the system, including the transformer's kVA rating and impedance, the conductor sizes and lengths, the ratings and impedance of overcurrent protection devices, and the characteristics of any loads connected to the system. Using this data, you can create a detailed model of the electrical system and calculate the fault current at any point in the system. Software tools are commonly used for this purpose, as they can handle the complex calculations and modeling required for thorough fault current study. These tools typically use iterative methods to solve the equations that describe the behavior of the electrical system under fault conditions. The importance of accurate fault current calculations cannot be overstated. High fault currents can cause significant damage to electrical equipment, leading to costly repairs and downtime. They can also pose a serious safety hazard to personnel. By accurately calculating fault currents, engineers can select appropriate overcurrent protection devices such as circuit breakers and fuses that will safely interrupt the fault current before it causes damage or injury. In addition to protecting equipment and personnel, accurate fault current calculations are also necessary to comply with electrical codes and standards. A National Electrical Code, or NEC, requires that electrical systems be designed and installed in a manner that will safely handle fault currents. This includes selecting equipment with adequate interrupting ratings and coordinating overcurrent protection devices to minimize the impact of fault. To summarize, if you only know the available fault current at the transformer but not the impedance or kVA, you cannot accurately calculate the fault current at a downstream location. The available fault current is a function of the impedance and kVA, and without knowing these values, you lack the necessary information to determine how the fault current will be affected by the impedance of downstream components. To accurately calculate fault currents, you must perform a comprehensive fault current study that includes collecting data on all the electrical equipment in the system and using software tools to model the system and perform the calculations. This will ensure that your electrical system is safe, reliable, and compliant with applicable codes and standards. Understanding these principles is essential for anyone involved in the design, installation, or maintenance of electrical systems. Accurate fault current calculations are a critical aspect of electrical safety and are essential for protecting equipment and personnel from the hazards of short circuits. So, the key takeaway is that while knowing the available fault current at the transformer is a useful starting point, it is not sufficient for determining fault currents at other locations in the system without also knowing the transformer's impedance and kVA. To calculate the fault current at a downstream point, you need to consider the impedance of all components in the fault current path, starting with the transformer's impedance and kVA and including the impedance of conductors, overcurrent protection devices, and any other relevant equipment. Therefore, the answer to your question is that you cannot calculate the fault current without knowing the impedance or kVA, even if you know the available fault current at the transformer.